How to find an element index in a sorted list with a binary search. So, actually I want to implement function which will find me the element index in a sorted list. And to search it, I will use a binary search. Okay, let's look at this function type signature. We have some ordering type A, and we have some list of these elements, and we have element which we want to find, and as a result we need to provide maybe integer. Maybe we can find this index, and maybe not, because this element can be not present in the list. Of course, I can start with the simplest case. What if I have just empty list, and no matter what I want to find, I can say that I can define this function as nothing, because I can't find any element in an empty list. But what if I have some list and I want to find some element E? For this I will use the helper function, which I call go. And this function will take two arguments. Actually, to continue searching, I need to know about okay. Okay, how we do a binary search? We split our list into two parts, the left and right, and also we take some middle element. On every step of iteration, we compare our searching element with this middle element. If if this element is equal, this means that we find our element. But otherwise, if our element is less or greater than the median element, this tells to us that we need to go to, we can go with recursion to the left part of the list or to the right part of the list. Okay, and if we go to the left part to the list, this is very simple. We just do our iteration process to the left part of the list. But if we go to the right part of the list, here we need to provide some information about how many elements this keep from the left, because here I want to return the index, so I need to know on every step how many number of elements I skip from the left part, and this means that I need to collect this information during the iteration and to pass it to the iteration, through the next iteration steps. Okay. This means that I need to provide some additional parameter to my helper function go, which carry the information about how many elements I skip. And at the first iteration, of course, I have the initial list and I have no elements skipped, and this means that I need to provide the 0 here, and also I need to provide my initial list to this function, and let's define this function go, this helper function. It takes the count of the count before, how many elements they have skipped before, and also we need to provide this list in which we do the searching of the element. And here we have some cases. What if my median element, I will define my middle element as ME. I will write this definition, how to define it later, but here at this point I can ask what if my middle element is equal to my element. In this case I can say that I found my element, and I can return the just because we have this maybe type here, and I need to how I build the index of the element which I find. I need to take the count before elements and the median index, and if I sum them, then I will have the correct index of my element which I find. Okay, but also we have some two cases here. If our element is greater than median element when they need to write something, and if my element is less than my median element, we also need to write something. Okay, what if my element is but no, let's start from the simplest case. What if my element is less than my middle element? This means that I need to continue my search in the left of the list, and I run, I call this function here again, and I need to provide the how many elements I have before. I have I state this number of elements same, so I don't need to modify it. I need just to pass it to the next iteration step, and of course I need to provide the left part of my list XL. I will define this left part a little bit later. But what if I have this right case? Then I need to search element from the right. In this case I need to do my iteration again, but I need to of course, because I go to the right, I need to modify the count before, because I have skipped the whole left part and one middle element, which means that I need my count before and add to it the length of the left part which I skip, and do plus one element, actually the middle element. And of course I need to provide here the right part of my list. Okay, this is the main logic, and here of course I need to do the definitions of my median index, of my x left, x right lists, which built from the main list. And to do this I can use I can use the split add function, which have this type signature. It takes some list, some index, and split this index into two parts, into two lists. Okay, and using this I can use this function to with my median index and my initial element x, and I will have the result. And this result I can in pattern match with, I can extract the left part and the right part. And also from the right part, I unpattern match the whole list. I will take the head of it. This is the median element. And the last thing here, they need to define the median index. And this is very easy. We need to take the length of our list and divide it by 2. And this will give to us our median index. Okay, I think this is correct definition, and we can try to compile it. Okay, let's load our file into GCI. It's compiled, and now let's try to run our function with some ordered list. I want to provide some ordered list, and what if I want to find the index of the 5? Okay, you can see this is a 4. And what if I have, for example, some duplicates ones here? And now the index of my 5 is 6, and I think this is correct. 0, 1, 2, 3, 4, 5, 6. Yes, this is correct result. Of course, I can find the index of 1, and here I will take the 2. As you can see, here I have 3 ones, but this algorithm returned me the last one. Oh, actually not last, in the middle. But what if I have here some duplicates too? In this case, I will receive the first duplicate. So here they have some randomness of the index, but we will actually we will find the correct index of our searchable element. Okay. So here in this algorithm, actually we have no guarantee that we will find the index of the first element which equals to our element which we want to find, because they have this this condition here, the first, and then we find the first which equal when they return our result. But in this case, if we find the element which is equal to our searchable element, we can have the case when there is some equal elements from the left of this median element, and actually to modify this algorithm to find the first left the first element which equal to our searchable element, and if we want to find it with a minimal index, we need to modify a little bit our algorithm by doing the so we need to, in this case, for example, we need to continue our process to search to the left, in the hope that we can find the some elements from the left part of the list. And of course, I think we need to here to provide some additional information about the so here we need to provide some parameter about the element which we find the first at first point. Okay, so we do a binary search with a list, but next thing I want to do is to do the binary search with a binary search tree. Okay, let's define it like this, but here I already have this definition. I just want to import this module here. And of course I will have in my namespace this definition of this binary tree. And now let's create function binary search which takes some orderable array and an element like our first implemented function, but as a result I want to define a binary tree of this type A. Okay. Sorry, what I'm saying. We take the binary tree, not list, we take a binary tree and we take this element and we produce some type which tell us the position for this element. But how can we define this type? How can we define position of the element in a binary tree? Okay, we define it by the sequence of steps where we go left or right in the tree to locate this element. And I want to define this type. I will call it D directions. And this type I have two constructors, empty constructors, either left or the right. So and here I want to define a list of these directions. Okay, and this list gives me the exact location of my element, and of course I can then I can have no result. In this case I want to take a maybe type. Okay, and I think we can do the implementation now. So if I have empty tree, okay, we have this empty constructor here, I can catch this case. No matter the element I want to find, I have nothing as a result. But if I have some tree constructed with a node constructor like this, and we have the element A, and we have left and right branch of this tree, and of course the search for some element E. Okay, in this case they have, of course we need the helper function here because we must collect the directions during our iterations. And I will call this function go as in the first implementation. Okay, and we need to initialize this function with with start parameters. And what is the parameters of this function? The first parameter is a empty list, because at first step they have no list of directions and they start with the empty list. And the second parameter is a tree itself. Of course, I think I didn't need this pattern matching here, and I will call my tree T. And that's all, I think. Now I can define my function. I will define it like this. And here, of course, I need to do a pattern matching of my tree. And my list of results, I will call it, let's call it final results. And how we do the implementation. So I think here I need to do some guards. If our A is equal to element E, which we want to find. In this case, we can return our result F. We didn't need to go left or right, we find our element. But what if we have that our current element is greater than our element which we want to find? In this case, we need to do the iteration again, but we need to add the right direction, because we go to the right and we add it to our result F. Okay, this is the first parameter of our function, and because they go to the right, they take the right subpart of the tree. And of course, if our element A is less than our element, searchable element, then we do exactly the same, but we go to the left and we go to the left. And I think this is all cases. But not, of course, this is not all the cases, because at some point our go iteration process will can lead us, if we not find the element, to the empty case of the empty tree. And in this case, how we define our go function. We defined our go function, of course, as nothing. This means that we go to the empty list, and by this way we didn't find any element. Okay, I think we can try to load our function. Okay, we have some errors. Of course, here I need to wrap my result as just, and the done. Now to check this function, of course, I need to provide the binary search tree for it. Okay, let's do the some comments at first. Binary search in BST, and this is we have the find element index in a sorted list, the binary search. Binary search. Okay. And of course, I want to implement function the next step, which will give me the binary search tree. So I will construct this tree from a list. Let's call this function build. It takes some ordinable a, and it's take a list from which I want to construct my tree, and it will produce me a binary tree. Okay. Let's start from simplest case. If they have empty list, they have empty tree. And now what I have the case, then my list is not empty. How can I construct the binary tree from it? But no, I think it's we can do it. Okay, at first we need to. I don't need this case here. At first I need to implement the ins function, which takes the element, just element, not a list, and insert it into a binary tree. And using this insert function, I can do the build function by folding. So I will fold my leaves to this insert function as and an empty tree as an initial element. Okay. How we do the insertion? We have this element as the first argument and the tree in which we want to insert the element. If our tree is empty, then we just create a node, this element into empty branches. But if our tree is not empty, we have some element A and left and right branch here, then we go to some cases from here. If our element A is greater or equal than our element E, when our tree stay the same in the node and in the left branch, but they do the insertion into the we do the recursive insertion into the right branch. Okay. And if our A is less than E, when they do the insertion into the left branch. Okay. And yes, I think this is correct. We can try to recompile this, and it's compiled. And now, as I said, I can do the build with my fold function. Which function? I think we can use fold L function. So here they have some I think better to use fold R function. because here they have b as a second argument, and we have our tree in our insert function as a second argument. So how can I define the build? Build is a fold R function which take our insert function. It takes some empty tree on result, and of course they need to provide some list which we pass to fold R function. Okay, and I think this should work. Let's check this. It's compiled. Now let's try to build a tree from a list of elements. So you can see they have this tree. Of course, it's not balanced tree. But why we have the greater elements from the right? I expect them from the left of the tree. Here we have, I need to swap the A and E, because I check my inserted element. If it's greater than the current element, then they go to the right, and otherwise they go to the left. Okay, let's reload. And now you can see that all the tree goes to the left. And now I can use this build tree to do the binary search. Okay, let's do the binary search on this tree, and we will provide the element that you want to find, for example 2. Okay, I need to derive show. Deriving show for this type to print my list of directions. Okay. So let's reload. And let's run. And you can see nothing. But why we have nothing here? Of course I have nothing here because I also need to swap this A and E. If our element is greater than the current element, then they go to the right, and otherwise they go to the left. Yes, you can see that to find 2, I need to do the left, left, left direction. And if I want to find 1, I need to do 4 left directions. If I want to find 5, I don't need to do any direction. The 5 is in the root, and that's why we get the empty list. But let's try to build some other tree. For example, let's change the order here like this, and we will have this tree. Now let's try to find 2, for example, but in this tree. So we have 3, 2, 1, 4, 5. And you can see here they have left, left, and then to right. So we need to, here they need to read our list from right to left. But of course I can fix this. They have the reverse function which reverse our list, and I can reverse my results. So here I call this go function, and I think I didn't need this case here because it's catch inside the go function. So the go function returns to me the maybe type. This means I can use functor here to access to the inner value with my reverse function, like this, I think. Let's try to reload, and so we have this tree, and we have this result. So we go to the left, and then to the right to find our 2. If you want to find 3, we go 2 steps to the left and 2 steps to the right. Okay,